What happens when the last star dies? Picture this, a universe so old that every galaxy has faded to black. No more sunrises. No more stellar nurseries giving birth to new worlds. Just an endless expanse of cold, dark space, punctuated only by the faint glow of dying embers that were once mighty suns. This isn't science fiction. This is the future of everything we know. Our universe, for all its beauty and complexity, is not eternal. The stars that light our nights, the galaxies that spiral through the cosmic dance, even the very fabric of space and time itself, all of it is temporary. But here's what makes this story extraordinary. The journey to that final moment spans timescales so vast they defy human comprehension. We're talking about billions upon billions of years numbers, so large that the entire history of our species becomes less than a blink of an eye. Tonight we're embarking on the ultimate voyage, a journey through deep time itself, following the universe from its vibrant present all the way to its final breath. We'll witness galaxy collisions that unfold over billions of years, watch as the last stars flicker out, and peer into futures so distant that physics itself begins to break down. This is the story of endings. But perhaps, if we look closely enough, it's also the story of beginnings. Let's start our journey in what cosmologists call the near future. And by near, we mean the next 100 billion years at time span that dwarfs the entire age of our universe so far. In just 5 billion years, our own sun will begin its death throes. It will swell into a red giant consuming Mercury and Venus, turning Earth into a molten wasteland before finally shedding its outer layers and collapsing into a white dwarf, a stellar corpse no bigger than our planet, but containing the mass of our sun. But our sun's death is just the opening act. In about 4.5 billion years, something magnificent and terrifying will happen. Our Milky Way galaxy, home to hundreds of billions of stars, will collide with its nearest major neighbor, Andromeda. Don't worry, despite containing over 1 trillion stars combined, these galaxies are so vast that individual stars will rarely collide. Instead, they'll dance around each other in a cosmic ballet, their combined gravity reshaping both galaxies into something entirely new. Astronomers call the result Milkomeda. It will be a massive elliptical galaxy, settled and mature, with most of its star formation already behind it. By the time this merger is complete, the universe will be entering middle age. But even Milkomeda won't last forever. As the universe continues to expand, driven by the mysterious force we call dark energy, galaxies will drift apart. The night sky will gradually empty. Future civilizations, if they exist, will see fewer and fewer stars each passing billion years. The universe is becoming lonelier. Now, let's fast forward to about 1 trillion years from now. By this point, something profound has happened. The universe has expanded so much that the cosmic microwave background, the afterglow of the Big Bang, has been stretched to wavelengths longer than galaxies themselves. The evidence of our universe's fiery birth has been erased by time. More importantly, star formation has essentially stopped. The gas clouds that birth new stars have been either consumed or scattered. The universe has used up its raw materials. The stellar nurseries have closed forever. This marks the end of the Stelliferous era, the age of stars. For about 13 billion years, stars have been the universe's primary source of light and energy. They've forged the heavy elements in their cores, warmed planets, and made life possible. But now that cosmic engine is winding down. The stars that remain are mostly red dwarf, small, dim, but incredibly long-lived. These stellar light bulbs will continue burning for trillions of years, but even they cannot burn forever. One by one, they'll exhaust their fuel and fade away. As we approach the 100-trillion-year mark, the last red dwarf stars begin to flicker out. The universe becomes a much darker, colder place. What remains are the stellar corpses. White dwarfs, neutron stars, and black holes. These objects don't shine with their own light. They only glow faintly as they slowly cool down. But this isn't the end of our story. It's barely the beginning. Welcome to the black hole era. We're now so far in the future that the numbers become almost meaningless to human minds. We're talking about 10 to the 40th power years from now. That's a 1 followed by 40 zeros. To put this in perspective, there are only about 10 to the 80th power atoms in the observable universe. In this unimaginably distant future, black holes have become the dominant structures in the cosmos. They're the last remnants of a universe that once blazed with the light of trillions of stars. Some are small, the mass of our sun compressed into a sphere just a few miles across. Others are supermassive monsters, containing billions of solar masses, slowly wandering through the void. These black holes didn't appear overnight. They've been growing for eons, occasionally feeding on the stellar remnants that venture too close. When two white dwarfs orbit each other, they slowly spiral inward, their gravitational waves carrying away energy until they finally merge in a brilliant flash, one of the few remaining sources of light in this darkened universe. But even black holes, these seemingly eternal gravitational prisons, are not immortal. In 1974, Stephen Hawking made one of the most profound discoveries in theoretical physics. He showed that black holes actually emit radiation, incredibly faint, but real nonetheless. Here is how it works. At the event horizon of a black hole, quantum mechanics allows particle pairs to spontaneously appear from the vacuum. Normally, these pairs would annihilate each other almost instantly, but near a black hole, something different happens. One particle falls in while the other escapes. The escaping particle carries away a tiny amount of the black hole's mass energy. This process, called Hawking radiation, means that black holes slowly evaporate. The smaller the black hole, the faster it evaporates. A black hole with the mass of our sun would take about 10 to the 64th power years to completely disappear. Time span so vast it makes the current age of the universe seem like an instant. But the supermassive black holes, the giants that once lurked at the centers of galaxies, they'll take even longer. We're talking about 10 to the 100th power years, a googol of years. These numbers are so large they begin to lose all meaning. If you wrote them out, the zeros would fill books. As the black holes slowly shrink, something fascinating happens. The smaller they get, the hotter their Hawking radiation becomes. In their final moments, they don't fade gently into the night. They explode in a brilliant flash of energy, the last light show in a dying universe. During this era, time itself takes on a different character. Seconds, minutes, and years become meaningless units. The only meaningful measure of time is the slow tick of quantum decay, the gradual dissolution of matter itself. But even in this seemingly dead universe, strange things might happen. Some physicists speculate about quantum tunneling events, so rare they occur only once in times much longer than we've been discussing. A white dwarf might spontaneously collapse into a neutron star. A neutron star might suddenly transform into a black hole. These are ghost events in a ghost universe. There's another possibility that sounds like pure fantasy, but is grounded in real physics. Given enough time, and we're talking about times so long they dwarf everything we've discussed so far random, quantum fluctuations might occasionally arrange themselves into something organized, a brief flash of complexity in an ocean of entropy. Some scientists have calculated that given enough time, quantum fluctuations could randomly assemble into a brain, complete with memories of a life never lived. These Boltzmann brains would exist for just a moment before dissolving back into chaos. But in a universe with infinite time, such impossible things become inevitable. The black hole era is not just about death and decay. It's about the universe exploring every possible state, no matter how unlikely. It's a cosmic game of chance played out over timescales that make eternity seem brief. As the last black holes finally evaporate in brilliant flashes of Hawking radiation, we enter the final phase of our universe's history. The age of heat-death approaches. We have now traveled so far into the future that the concept of years has lost all meaning. We exist in a time beyond time where the universe has settled into its final state, maximum entropy. This is the heat-death of the universe, though the name is misleading. It's not that everything has become hot, quite the opposite. The universe has reached a state of perfect thermal equilibrium, where temperature differences have been erased and no more useful work can be done. It's a cosmic equilibrium, silent and still. What remains in this ultimate future? Mostly empty space punctuated by the occasional elementary particle electrons, positrons, neutrinos, and photons stretched to wavelengths larger than galaxies once were. These particles drift through the void at temperatures approaching absolute zero, rarely interacting, barely aware of each other's existence. The universe has become a thin, cold soup of the most basic building blocks of reality. No structure remains, no complexity, no information processing. The cosmic story that began with a bang has ended not with a whimper, but with silence. But even this isn't quite the end. In this far future, time itself becomes strange. With no clocks, no processes, no changes to mark the passage of moments, does time even have meaning? Physicists debate whether time can exist without change, whether duration has any significance in a perfectly static universe. Yet even here, in this ultimate emptiness, quantum mechanics whispers of possibilities. Virtual particles still flicker in and out of existence. The quantum vacuum still bubbles with energy fluctuations so small they barely qualify as events. These might be the last remaining traces of dynamism in an otherwise frozen cosmos. Some theorists suggest that given enough time, and now we're talking about times so vast that our previous incomprehensible numbers seem small, even protons themselves might decay. The very atoms that make up matter could slowly dissolve into energy, leaving behind only leptons and photons in an ever-expanding void. If protons do decay, and we're still not certain they do, then even this final inventory of the universe is temporary. We would eventually reach a state where only stable leptons, electrons, positrons, neutrinos, and massless photons remain. These particles would continue their lonely journey through an ever-expanding, ever-cooling space. But here is where our story takes an unexpected turn. The heat death might not be the final chapter after all. Modern physics suggests several alternative endings to our cosmic story, each stranger and more profound than the last. While heat death represents the most likely fate of our universe based on current observations, it's not the only possibility. The cosmos has several other dramatic endings up its sleeve, each dependent on the true nature of the mysterious forces that govern reality. Let's explore the Big Crunch, perhaps the most poetic of all cosmic endings. This scenario unfolds if dark energy, the force currently accelerating the expansion of the universe, somehow weakens or reverses. Instead of expanding forever, space itself would begin to contract. At first, the change would be imperceptible. Galaxies would slow their recession from each other, pause, and then begin to approach. The cosmic microwave background radiation would start to heat up as it gets compressed. Stars long dead would be reunited with their siblings across the void. As the contraction accelerates, galaxies would merge not through gentle collisions, but through violent, inevitable convergence. The night sky would brighten as distant galaxies' blue shifted toward us. Eventually, individual galaxies would be torn apart by the increasing density of space itself. In the final moments, everything, every atom, every particle, every quantum of energy would be compressed back into a singularity. The universe would end as it began, in a point of infinite density and temperature. Some physicists speculate this could trigger a new Big Bang, making our universe part of an endless cycle of death and rebirth. But there's an even more dramatic possibility: the Big Rip. This scenario emerges if dark energy continues to strengthen over time. Rather than simply expanding forever, space itself would accelerate its expansion until it overwhelms all other forces. The Big Rip unfolds like a cosmic horror story in reverse. First, galaxy clusters would be torn apart as the expansion of space exceeds the strength of gravity holding them together. Then individual galaxies would dissolve, their stars scattered into isolation. As the expansion continues to accelerate, stellar systems would be next. Planets would be ripped away from their stars and sent careening into the void. The expansion would then overcome molecular bonds, tearing apart planets, asteroids, and eventually every solid object in the universe. In the final moments before the Big Rip, even atoms themselves would be destroyed. Electrons would be torn from their nuclei, protons would be separated from neutrons, and ultimately even the quantum fabric of space-time itself would be shredded. The universe would end not with a whimper, but with the total destruction of everything that ever existed. Then there's perhaps the strangest ending of all: vacuum decay. Our current understanding of physics suggests that the universe might exist in what's called a false vacuum, a stable state that isn't actually the lowest possible energy state. It's like a ball balanced on a hill stable for now, but not in the deepest possible valley. If this is true, then quantum fluctuations might occasionally create a bubble of true vacuum somewhere in the universe. This bubble would expand at the speed of light, converting false vacuum to true vacuum as it grows. Inside this bubble, the laws of physics themselves would be different. Matter as we know it couldn't exist. The terrifying beauty of vacuum decay is its inevitability and invisibility. We would have no warning. The bubble would arrive at the speed of light, instantly rewriting the rules of reality. Everything we know would cease to exist, not destroyed, but retroactively impossible. Yet even vacuum decay might not be truly final. The new vacuum state might have its own physics, its own possibilities for structure and complexity. Perhaps new forms of matter and energy would emerge, as alien to us as we are to the quantum foam from which our universe first emerged. These alternative endings remind us how much we still don't know about our universe. Dark energy remains mysterious. The true nature of quantum gravity eludes us. The ultimate fate of everything depends on discoveries we haven't made and physics we haven't discovered. As we contemplate these vast timescales and ultimate endings, we're confronted with profound questions that blur the line between physics and philosophy. What does it mean to exist in a universe destined to end? How do we find meaning in a cosmos where everything we build, everything we are, will eventually fade into oblivion? These questions have haunted humanity since we first looked up at the stars and wondered about our place in the cosmos. But now, armed with scientific understanding of the universe's far future, they take on new urgency and complexity. Some find the universe's ultimate fate deeply disturbing. The philosopher Bertrand Russell once wrote about the unyielding despair that comes from recognizing the temporary nature of all human achievement. If the universe will eventually reach a state where no trace of our existence remains, where even the atoms that make up our bodies will have decayed away, what's the point of anything we do? But this perspective, while understandable, might be missing something crucial. The universe's far future doesn't erase the meaning of the present, it might actually enhance it. Knowing that stars are temporary makes each sunset more precious. Understanding that consciousness is rare in the cosmos makes every moment of awareness more significant. There's also the question of what consciousness itself means in this context. Could intelligence, in some form we can barely imagine, survive even the heat death of the universe? Some physicists have explored scenarios where advanced civilizations might find ways to continue information processing, even as the cosmos approaches maximum entropy. Freeman Dyson proposed that by slowing down their thoughts and metabolisms, intelligent beings might experience an infinite number of subjective moments even as the universe approaches its final state. They would think increasingly slowly, entering longer and longer periods of hibernation, but their total experiences would be unlimited. Other scientists have suggested even more exotic possibilities. Could consciousness somehow transfer itself to stable particles like electrons? Could information be preserved in the quantum fluctuations of empty space? Could intelligence find ways to tunnel between universes, escaping the death of our cosmos entirely? These ideas stretch the boundaries of known physics, but they represent something profoundly human. The refusal to accept endings as final. Throughout history, humans have sought ways to transcend mortality, to find permanence in an impermanent world. Now we're extending that search to cosmic scales, but perhaps the most profound implication of the universe's far future is what it tells us about now. We exist in the universe's golden age, the brief span when stars shine, when complexity is possible, when consciousness can emerge to contemplate its own existence. We are the universe becoming aware of itself, even if only temporarily. Consider this. Every human who has ever lived, every civilization that has ever risen, every work of art ever created, every moment of love ever experienced, All of it happens during the tiniest sliver of cosmic time. We are participants in the universe's brief moment of awakening. This perspective doesn't diminish human significance, it amplifies it. We are not insignificant because we are small and temporary. We are precious because we are rare and fleeting. We are the cosmos dreaming of itself, if only for an instant. As our journey through deep time nears its end, we find ourselves confronting not just endings, but the possibility of beginnings. The universe might be more resilient, more creative, and more mysterious than even our boldest theories suggest. Consider the cyclical models of cosmology. If the Big Crunch scenario is correct, our universe's death might birth a new cosmos. The same forces that created the Big Bang might repeat infinitely, each cycle producing new stars, new galaxies, new possibilities for complexity and consciousness. We might be living in one chapter of an endless cosmic story. Even in the heat-death scenario, quantum mechanics suggests that given infinite time, incredibly unlikely events become inevitable. Random fluctuations might occasionally organize themselves into pockets of low-entropy brief islands of complexity in a sea of equilibrium. These fluctuations might even recreate something resembling our current universe, complete with stars and galaxies, a rising phoenix-like from the ashes of the old cosmos. String theory and modern cosmology suggest even more exotic possibilities. Our universe might be one of countless others in a vast multiverse. While our particular cosmos might face heat-death, new universes might be constantly born through eternal inflation, each with its own physics, its own possibilities, its own eventual fate. Some theories propose that black holes might be gateways to new universes. Every stellar collapse that creates a black hole might simultaneously give birth to a new cosmos on the other side of the event horizon. If this is true, then the universe's capacity for creation extends even beyond its own boundaries. There's also the profound mystery of consciousness itself. We still don't understand how matter gives rise to subjective experience. Could consciousness be more fundamental than we realize? Some scientists and philosophers have suggested that awareness might be woven into the very fabric of reality, surviving even the destruction of the brains and computers that seem to generate it. These ideas remain highly speculative, but they remind us how much we still don't know about the nature of existence. The universe has surprised us before with dark energy, with quantum mechanics, with the emergence of complexity from simple rules. It will undoubtedly surprise us again. Perhaps the most important lesson from our journey through cosmic time is this: endings and beginnings are often the same thing, viewed from different perspectives. The death of stars creates the heavy elements necessary for planets and life. The collision of galaxies triggers new waves of star formation. Even the heat death of our universe might be the necessary prelude to something unimaginably new. When the last star finally dies, when the final black hole evaporates into the void, when the universe reaches its state of maximum entropy, we might not be witnessing an ending at all. We might be seeing the moment before a new kind of beginning, one that our current physics cannot even imagine. The universe has been creating and destroying for nearly 14 billion years. It has transformed hydrogen into stars, stars into galaxies, and galaxies into the vast cosmic web we see today. It has given rise to planets and life and consciousness. It has created beings capable of contemplating their own existence and the fate of everything that is. This creative power, this ability to generate complexity, beauty, and meaning from simple initial conditions, might not be limited to the cosmic eras we can currently observe. The universe's capacity for innovation might extend far beyond the heat death, far beyond any ending we can conceive. So when we contemplate the far future of the cosmos, we're not just witnessing the universe's death throes. We're glimpsing the universe's infinite creativity, its endless ability to find new ways of being, new forms of existence, new chapters in a story that might truly have no final page. The end of time might not be an ending at all. It might be the universe's way of turning the page, preparing to write a new story in a language we have yet to learn. When the last light fades, what remains is not silence, but the eternal possibility of new beginnings.